Let's review a method of solving systems of equations, linear equations, using matrices instead of the whole expression of the equations. We will use elementary row operations with the help of a web program called a web page. Linear Algebra Toolkit will provide to the web page the coefficients of our system of equations, as you see there. To go to the web, just write in Google or wherever your search engine is with the keys Linear Algebra Toolkit. And there are many people using or giving links to this page, but I suggest you to go to MAA organization, that is the Mathematical Association of America, and choose Linear Algebra Toolkit. Even that it doesn't look that neat, it gives you a very good link to Linear Algebra Toolkit, here, and you are now in Linear Algebra Toolkit. Just enter and choose Row Operation Calculator, and here we are. Since we are going to enter this matrix, the augmented matrix of the system is called augmented because it has the matrix of the coefficients or the coefficients of the systems to the left, augmented by the parameters to the right. Then this is called the augmented matrix of the system. And then we tell Linear Algebra Toolkit that we are going to use a matrix 3 rows, 4 columns. 3 rows, 4 columns. Number of rows, 3. Number of columns, 4. And submit. Now, let's give to this web page the numbers that we have here. 1, 1, minus 1, 0. First row, 1, 1, minus 1, 0. Second row, 1, 2, 1, 5. 1, 2, 1, 5. Third row, 1, 1, 1, 4. 1, 1, 1, 4. And go, submit. Here you have the matrix, Here is the matrix. And then we are using elementary row operations. Using the first row, we are going to do any elementary operation to get 0 here and 0 here. And I say, if I add minus 1 times the first row to the second, I'll get a 0 here. Let's do it. There is the 0 there, And I say again, if I add minus 1 times the first row to the third, I'll get a 0 here. Then minus 1 times the first row to the third row, do it. And I have this 0 there. Then I got, using this pivot, I have a column with 1 in the corner and zeros down here. And then go ahead and use this entry, the second row, to get a 0 here and a 0. Okay, the 0 here is free, we got it without asking for. But we want to go, we'll use the method of gauss-Jordan to have the pivot and get zeros in the whole column, but in the pivot. 0 here, and I say if I add -1 times the second row to the first, I'll get a 0 here. Add -1 times the second to the first, and do it. I get 0, 0. And then go to the third row. It's much more better to work with ones than with twos. Then multiply this row by 1/2 to get 1 and 2, and 1 here. Then multiply the third row by 1/2 to get a 1 in the pivot that I'm going to use. Here, do it. Here it is, the 1. You don't need the 1, but the Gauss-Jordan method asks you to get ones in the main diagonal. Then with this, you still can have 0 here and 0 here without affecting this part of the matrix with zeros. Then you say, if I add 3 times the third row to the first, I'll get a 0 here. If I add -2 times the third row to the second, I get a 0 here. We have to do it in 2 steps. Add 3 times the third to the first to get a 0 here. 3 times the third row to the first, and you have it. You know, the pivot and zeros here. Now add -2 times the third row to the second and get a 0 here, you know. Then add -2 times the third row to the second and get a 0 there. Here it is. Now you have the pivots in the corners. From left to right, they are moving to the right, which is called an echelon matrix, escalones. And then you now have that the original system that you are solving is equivalent to x plus 0y plus 0z equal 1, 0x plus y plus 0z equal 1, 0s plus 0y plus c equal 2. And then you got the solution of the system. That is x equal 1, y equal 1, and c equal 2. And just one solution. It is a system compatible, independent. Just one solution. Try the solution here. 1, 1, 2 for x, y, z. 1, 1, 2, and check. S plus y minus c equals 0. S plus 2y is 3, plus c is 2, 5 equal 5, and then x, what is 1, plus 1 is 2, plus 2 is 4. Very good. It is the solution of the problem.